The goals of this project are simple: manage cost of changing charging stations, minimize the number of unused charging stations, minimize the waiting time of the vehicles to charge, and manage the power being delivered to the whole system. Our environment is accessible, all the agents can obtain complete, accurate, up-to-date data about the smart grid, non-deterministic, an action has no single guaranteed effect, dynamic, the world changes while the agent is deliberating, discrete, we have a finite amount of actions, non-episodic, events have a direct correlation to other events, random, environment has random events such as crisis, costs, agents have a cost of energy or money for each iteration. Now let's talk about our agents. First of all, the driver assistant. The agent's emotional behavior is very simple. The agent holds a state that simulates how much it likes the station. This variable will be used in the decision making of which station the agent decides to go to charge his car. The driver assistant must decide which station he wants to go to charge his car. This decision is based upon his preference for the queue waiting time, the distance and the price of a charging station, as well as its emotional value. Then it's computed a rating based on these values for each station. The agent chooses the station with the highest rating. It's important to note that the decision of where to charge the car is not final, since on the way there and while being on the queue to charge, the agent may reconsider its choice and thus choosing another station. This is possible since the charger handler sends proposals to driver assistants that need to charge their battery, and that proposal may be better than the choice it previously made. Speaking of charger handlers, they are integral agents of our system, since they are the ones who charge the cars of the driver assistants. As stated above, the charger handler sends proposals to driver assistants in order to avoid all cars choosing the same station. Usually, this agent doesn't have enough energy to supply all its clients, therefore communicates with the power operative that decides how much energy it can give to him. Another important aspect of the offers and negotiations of the charger handler is that the fact that the charger handler can be turned on or off. Power operative is critical in our solution because we want to evaluate if the system can survive outages. This is even more important nowadays with a pandemic like COVID-19. Our solution only tests small outages of 1 tick, but we wanted to test a large number of breakdowns in the system and evaluate its performance. The main goal of the power operative is to give energy from the energy provider and give it to the needs of each charging station. To simulate a realistic scenario where the source of energy can be unstable, we opted to simulate two kinds of problems: power outages and power redistributions. The first one provides no energy to the system, and the latter provides a diminished amount. This is what the energy broker tries to simulate.
Here we can see a simulation of our projects. Let's decompose this simulation. The circle symbolizes the vehicles, the inverted triangles the charging stations, and the black diamond is the power operative. The yellow square is the energy broker, and there is only one energy broker and one power operative. In our example, we use a simulation that has a map of the Alameda campus, but we show here different examples of maps, including in this case New York and in this case Lisbon. Then we push the start button. With this simple example, we can see a vehicle moving around until it needs to recharge. Check what happens when the vehicle is charging. Also, the energy broker can redistribute, that's the black cross, and have outages, the red cross. Now let's use a more complex example. Here we have an unstable simulation with 50% of outages and cars stop because the charger stations have no energy to charge them. At the left we can see a graph that shows us the increase in the death cars over time. This is expected because of the 50% of outages.
And even with this many outages, we can still make profits.
Because of the good management of the power operative, some cars manage to survive. Cars can also revive when they stop near a station that had no energy but eventually get energy and can charge them, as we are seeing. The driver assistant is an emotional agent that has preferences, and maybe it chooses a distant charging station.
However, these stations can still try to convince the agents to go there, using a bidding system.
The Apocalypse Outage is a destructive scenario where there are a lot of outages and cars stop because they don't have charging stations with energy. The graph shows us that the dead cars increases.